So in this video, I will talk about the application of resampling in R. Please remember that these resampling methods involve repeatedly drawing samples from a training set and refitting the model of interest on each sample in order to get that additional information about the fitted model in here. And first one is going to be leave one out of cross-validation. And it also includes splitting the data set of observations into two parts in here. But instead of that comparable size of training and test data, we get a single observation. And maybe I should show this one for you. In this leave one out cross-validation, we also call that n-fold cross-validation. For each step, we are just having single row in that one. And of course, since we have n number of observation, we have n-fold in here. And the remaining test, I mean this part, remaining part is going to be training set in here. Okay, and the statistical learning method is fit on this n-1 training observations. And we are going to do our predictions, which are y-hat, for the excluded observations in here. And we are repeatedly doing that part in this cross-validation. And let's see what can we do in R, which libraries we are using or which methods we can use in here. And for this example, we are going to use our library ISLR, which is the library of our book in here. And let me just add the name of the book one more time. Okay. Here is the book we are using for this lecture. And so in this library, there is one data set, which is auto data sets. And so it is this auto data sets, and you can see that it shows gas mileage, horsepower, and other information for 292 vehicles in here. And it's in data frame formats, and you see that, for example, there are some variables in here like mpg, which is miles per gallon, and we have cylinders, horsepower, weight, year or name, and here is the source of these data sets. And we will use mpg as our response variable. And if you want to see the data sets like in a brief way, you can just see the first 6 lines of whole variables. And mpg is going to be our response variable. And we will try to see the relationships between this variable and the explanatory variables. And first thing we can do is that one of the basic topics, we can just run a linear model. And let's see how we can implement it in R. I want to give a name to my model, glm.fit. Instead of lm, we can just use glm and mpg versus, as a first explanatory variable, we may want to use horsepower. Okay, this is the first one. And you should also define your data set, which is auto. And if you do not add any more options, it's going to run a linear model for you. Okay, I run this one and I want to see my coefficients for glm.fit. Here are my coefficients. I see my intercepts and also horsepower parameter in here. And you may notice that there's a negative linear relationship between this horsepower and mpg. Okay, and we may want to use a cross-validation method to see how well our model is working in here. And for this one, we should use another library. Let's see, I want to use boot library in here. Okay. And we will use the same GLM function, a linear model, and I want to use cross-validation function in here. So what will happen that you are going to give your data sets, and this function calculates the estimated k-fold cross-validation prediction error for your generalized linear model, okay? And so we just run the function with our data sets. Please remember, it's just asking the data set as a first option. And then we should give our model. We are going to use GLM fit in here. Let me just save the error in somewhere. When you run that one, you will see, so we should just get the delta. Not all of them. Here are two values in here. You see that these are our cross-validation estimates, which are defined before in here. This is our, so for each step, you please remember that we have n-fold in leave one out cross-validation. And for each step or for each fold, we are finding one MSE value. And our final product, which is test data cross-validation, is going to get all these MSEs and find the average value as our final product in here. And the second MSE is just very close to the first one. And mainly we use this guy. But this is just adjusted MSE to reduce the bias in here. Okay. So we can repeat this procedure for more complex polynomial fits in here. And let's see how can we use that part. Let's first generate a new vector that we are going to save our error values. And let me repeat 0 for 5 times because we will use 5 different models in here. And so in this example, we iteratively fit polynomial regressions for polynomials of order from 1 to 5. And then we will just find the related cross-validation errors and then stores them in this vector in here, in CV error, in this example. And we can just use for loops in this example. And let's see, I want to go for I in 1 to 5. Please remember, we are just using 5 different polynomials from 1 to 5 in here. And so first thing, I'm going to fit my model, GLM fit in here. So instead of LM, so we are going to use linear model, but instead of LM, we are just using GLM because GLM allows us to use also cross-validation in here. So if you do not add any options in there, GLM is going to work like LM in this context. And let's see, I have my MPG as response variable and horsepower as my explanatory variable in here. But instead of this guy, I want to use poly function because we are going to use different polynomial functions in here. And you should add your I in here. And for each step, R is going to change from 1 to 5. Okay. And so when we write this, maybe I should be here, I guess. When we write this one, we also should define our data sets, which is auto. Okay, this is the first step. And in our for loop, we are going to also find cross-validation error, which is an empty vector now. And for each step, I want to fill this vector by using cross-validation GLM function. And so in here, we have our data set, auto data set, and also glm.fit that we defined in the previous step. And so we just want to get the delta value, which is the cross-validation in here. And I want to just get the first value, okay? So I have my empty cross-validation error vector for each step from 1 to 5. We will just run one polynomial function. For example, the first one is just this one. And second one is just adding something like horsepower to the 2 in here, okay? And second model is going to be something like this one, horsepower in our for loop, I mean, okay? And it's going from 1 to 5 for each step, okay? And this is happening inside my for loop when I run this part. And if you want to see your final result in here, here is my error. For each step, you see that, for example, for the first one, it's 24.23. Then it's just reducing in here. And after a while, you see that we have this sharp drop in quadratic one. For example, if we use the quadratic form of our function, then we are getting a smaller error in a sharp drop in our estimated MSE in here. But we don't see any improvement from using higher order polynomials. Maybe we can just stop in here, okay? And I also wanted to show you something that instead of this guy, this for loop, mainly I don't use for loops frequently in R. I want to just add a sapply version of this for loop, okay? Also, instead of this guy, you can just use sapply, and from 1 to 5, it is going to run this function for I is going to 1, 2, 3, 4, and 5. And it's just doing the same job in here. And you will see that sapply is kind of a clearer way to show this for loop, and it's going to maybe run faster, okay? And then when we run this guy, you will see that we have exactly the same results in here. And I want you to see a plot that we already seen in the book before. And in here, we want to run these polynomial functions from 1 to 1 to 10. Let's see. Let's see. Okie dokie. Okie dokie. Let me just run this part and see how it is going to. So let me run this part. Okie dokie. So instead of 5, now I'm going from 1 to 10. We are using higher order polynomials in here. And we are just running the same function. First thing is our GLM, which is actually LM function in here. And we are just using just polynomial function in here. And each step, I'm just getting these MSEs, okay? And by using these MSEs, we are going to plot how it is changing with polynomial order in here. Okie dokie. And this is our function actually. And you will see that for different types of polynomial functions in here, we have a sharp drop. And after a while, we don't have that much difference, but in this polynomial order, we also have an increase in this part. Okay. Let's see. Maybe I should run this part. Yeah, this is not. I think this is just repeating itself. Maybe we should run this part first. This is not what I want to see. Okie dokie, we just run this part. Okie dokie, now it is the correct form. And now we are able to just run our plot. Yep, that's the correct one. And now we are going 1 to 10. And in here, you see that we have a decrease in this quadratic form. And after a while, we don't have that much differences. And now we can just go with the second order polynomial function for this data set. And let's save the file. So instead of leave one out cross-validation, we can use k-fold cross-validation. And so I want to use just k-fold cross-validation, and we still use that GLM function in here. I mean, the cv.glm function is also used to implement that k-fold cv. And so this approach involves randomly dividing the set of observations into k groups. I mean, in this k-fold. Okay. So in this method, we are just randomly dividing a set of observations into k group instead of n groups, or you can just call that as folds. And they are going to be approximately the equal size, okay? Let's use k, which is a hyperparameter in this method, as 10 in this example. And I just want to use the same data set, that auto data sets in here. Let's set C to get the same result for all of us. And now I want to save my error, like I'm going to get 10 of them by using my function. Again, I want to use sapply instead of for loop. This time I'm going from 1 to 10. For the function of I, we will repeat these steps, okay? And first one is our, let's just add here, cross-validation.glm. Okay. Please remember we should first give our data set. Then I'm going to run my GLM, okay? And mainly I'm using LM in here, MPG versus, and we will use horsepower as a predictor, but please use polynomial version in here, horsepower, and I will use it for each I. And so you should also define your data set inside, which is auto data set. And for this cross-validation, if you just define K, and it's going to run a k-fold cross-validation for you guys, okay? And in here, if you want to get the MSE values, please write delta, and we will just use the first one, okay? So let's repeat what is happening in this chunk of comment. We have cross-validation error.10 vector, and for each step we are going to get one value for this vector. Maybe I should just delete this part, keep it here, yeah. And by using sapply function, I'm going to run this part 10 times from 1 to 10. Just I is changing for each step. It's going to be starting with 1, and the last step is going to be 10 for I, okay? So we are just running cross-validation method and just collecting the delta at each step. And inside you have your auto data and you have your GLM function, and poly is used for your polynomial function in here, okay? When you add K as a parameter inside that GLM, or CVGLM, I mean, R is going to implement a k-fold cross-validation for you. Let's run. And maybe you notice that it is running really fast, that the computation time is much shorter than leave one out cross-validation. Maybe you should think about it, why it is much faster in here. I mean, just stop the video and just think about it. And you will see that we have different MSEs for different models. And this is the linear model with any polynomial term. And we have quadratic and cubic, and it's going different polynomial functions in here. And we still see a little evidence that using cubic or higher order polynomial terms in here because they're just leads to lower test error than simply using a quadratic fit. So in this example, I think I would go with quadratic fit in here. So we have seen that leave one out cross-validation and k-fold cross-validation. And we are good to go with the Bootstrap method now. And let's see, we are going to use Bootstrap for this example. And so portfolio data sets is going to be used for Bootstrap example. And you can find this example defined, I guess, in section 5.2 in our ISLR book. And that data set includes just past values of financial assets in here, okay? And we have 100 returns. They are simulated data set for 2 assets. X gives returns for asset X in here, and Y returns for asset Y. And we just use this data set to estimate the optimal fraction to invest in each asset to minimize investment risk in here, okay? And we have that combined portfolio. We will use Bootstrap to estimate the standard error of this estimate in here. And suppose you want to invest a fixed sum of money into the financial assets that yield returns of X and Y respectively, and where X and Y are random quantities. First, you should invest a fraction alpha of your money in X and will invest the remaining 1 minus alpha in Y. And since there is variability associated with the returns on these 2 assets, you should choose alpha to minimize the total risk or variance. And actually, you are going to minimize this guy in here. Okay, we are going to minimize this guy. And so we showed that we minimize the risk with this formulation. Actually, we don't know the true values of this variance, and we are actually going to estimate that alpha in our R code now. Okay, you can just find this part and detailed information in our ISLR book. Let's see. First of all, I'm going to write this function in R. Okay, and it is our alpha.fn function. Okie dokie. I have my function, and first thing I'm asking for the data, and then I'm asking for the index. Okay. And for X, we are having the data set, and then get X in here, and we will only have the ones that includes that index, and same for Y. And I have my data, and I'm going to get Y values in here for corresponding indexes. And return is going to be what? I have my variance of Y minus covariance of X and Y in here. And we have the variance of X plus variance of Y minus 2 times of covariance for X and Y. Okie dokie. This is my alpha function in here. First of all, I want to use 100 observations to estimate alpha, and we are going to use the data portfolio. Let's see if I write portfolio in here, you can see the same description that we have done before. And if you want to see the first 6 lines again, then you can just check out. We have only S and Y's. Okay, when you have the dimension of portfolio, you see that's going to be 100. That I want to get that 100 observations to estimate my alpha in here, which is alpha value, I mean the alpha FM function. And I'm going to give the data set, sorry, portfolio, and we want to get from 1 to 100 for that index in here, okay? We have data, we have index, and we are using all values, and the alpha value is 0.57, okay? And then we can use sample function to randomly select, like in Bootstrap, 100 observations from the range 1 to 100 with replacements, okay? So this is like constructing a new Bootstrap data sets and recomputing alpha hat based on these new data sets in here. Let's see what I mean. I want to use that sample function, but first let's just set seed as 1 to get same values for all of us, okay? And again, we are going to use that alpha.fn function, and for portfolio data set. This time, instead of all values, I'm going to sampling 100 from 100. Remember that Bootstrap sample size is going to be same as n. And you should do something which is important. You should say replace as true, because we are just doing sampling with replacements in Bootstrapping. And set seed is done. And when I run this part, you will see that now we have higher alpha hat in here, okay? So we can just implement a Bootstrap analysis by performing this command many times. We can just run this part many times for different seeds in here, and just collect that output several times and record all the corresponding estimates for that alpha. And then we can just compute to standard deviation. But if you just use boot function, this guy in boot library, and this just implement that job for you, okay? So let's see, let's just produce 1000 Bootstrap estimates for our alpha in here. I want to use my boot function again with portfolio. And now we should give our function in here that we already defined. And you should also define your R, how many times you want to do this bootstrapping. Let's say I want to just run that part 1000 times. And we are going to find Bootstrap 1000 Bootstrap estimates in here. You see that we have 1000 times Bootstrap, and it's just giving the Bootstrap statistics for us. And the final output shows that using that original data, alpha hat is going to be 0.57, and that the Bootstrap estimate for the estimate standard error in here is 0.09. So if you roughly speak in here, for a random sample from the population, we would expect alpha hat to differ from alpha by approximately 0.09 on average in here. We can also use that Bootstrap method to estimate the accuracy of a linear regression model. And here is what we can estimate the accuracy of a linear regression model. And the Bootstrap approach in here can be used to assess the variability of the coefficient estimates and predictions from a statistical learning method in here. So we will, in this example, we will use the Bootstrap approach in order to assess the variability estimates of beta 0 and beta 1. Please remember these are the intercept and slope terms for linear regression model. And I will use that auto data set one more time. and use horsepower to predict MPG. Okay, and at the end we will just get standard error for beta 0 and beta 1 by using these bootstrapping methods. Let's start first writing a function in here. And so I will create a simple function, and which is going to take that auto data sets and also a set of indices for the observations. And it's going to return the intercept and slope estimates for the linear regression model in here. Okay, so let's see what I mean. I have my boot.fm function. You can just give it another name. It's up to you guys. Okay. And here is my function. I'm asking for data and then index. Okay, then let's start with the function. I want this function to return coefficients of what? Coefficients of LM function. And please remember, we will use that auto data. And I want to predict this MPG by horsepower. Okay. And the data is going to be data we will supply for this one. And the subset is going to be the index that you will provide. Okay. And I have my function. Let's run this guy. Let's say I have my boot.fn function that we define. And we will use auto data sets, and it's going to go from 1 to 392. This is the sample size. Okay. And you see that it just gave us an intercept and that horsepower. Okay, that we already know these are the intercept and slope for parameters for our data sets. And so we can also use that function, that boot.fn function, to create Bootstrap estimates for the intercept and slope terms by randomly sampling from that observation with replacements. Okay, let's first define a seed. Let's say it is 1 to get the same value for all of us. We will use that guy, okay, to do some kind of bootstrapping. And we have auto data set. And I want just to get the sample from this data set. And it's going to get the same sample size of the data set, 392. And please do not forget to add replacement true, because in Bootstrap, we are just doing sampling with replacements. And when I run this part, you will see that we have slightly similar result for intercept and horsepower in here. Okay, and when you just run this one more time, you see you have something else. And so, of course, we maybe should change this part because now we have set seed as 1. Then we are getting the same. Oh, no. It's just first one. It's just running for set seed as 1, and you are having this guy in here. But when you just run this part several times, and you see that you're just having many intercept and slopes for your data sets, okay? And bootstrapping, for example, when you say 1000, bootstrapping is just running this guy 1000 times. And you can just run this function 1000 times and collect these values in here, okay, slopes and intercept, and try to find SE, standard error, for your estimations in here. But instead of this one, you can just easily use boot function to compute the standard error of 1000 bootstrap estimates for your intercept and slope in here, okay? I can just use boot function, which is defined in boot library. And here is my auto data, and I want to use my boot function that I defined it. And how many times? Let's say 1000 times, okay? When you run this part, you see that this time you have 2 values for your original values in here. And you see that you are getting your standard error in here. So this output shows that your Bootstrap estimate for standard error of beta 0 prediction is 0.84 in here, and the Bootstrap estimate for your standard error of beta 1 hat is 0.007 in this example. And so when we use this example, we can easily see that we may use this Bootstrap method to just estimate the accuracy of our linear regression model in here. And these are the references I use to prepare this video. Here are the references. And the second one is our ISLR book.